Greetings everybody, this is Dr. Gomez. This is the second video for the Chapter 9 Lecture Notes, and this is a very important topic. This deals with static equilibrium. And you're going to have at least one static equilibrium problem on exam 4 and at least one static equilibrium problem on the final. So you really want to make sure you understand this topic. And it's not terribly difficult, but, again, you're going to see it on exam 4 and the final. Well, in the language of physics, static means stationary, meaning not moving. Well, a rigid object, and by that we mean typically it could be like a rod, i.e. like some type of a pole that's supporting a sign that's hanging from a building. The pole is affixed to one end of the building. You hang a sign from the other end. It could be a construction beam that's attached to the side of a building, and the workers walk out on the beam to do their work. But a rigid object is in static equilibrium if it's not moving linearly, meaning the sum of the external forces acting on the object must equal 0. And it's in static equilibrium if it's also not rotating. And if an object is not rotating, that means that the sum of the torques acting on the object must equal 0. Because remember, what is a torque? It's a force that produces a rotation. Well, if the object is not rotating, there may be torques acting on the object, but they better add up to 0. Just like if an object's not moving linearly, there are going to be forces acting on it, but all those forces are going to add up to 0. Well, remember, force is a vector. So condition 1 for an object in static equilibrium, for condition 1, the sum of the external forces equals 0. Well, what does that mean? Well, that means that the sum of the forces acting in the x direction must be equal 0. The sum of the forces acting on the object in the y direction must equal 0. And typically we won't see this in this class, but the real world is three-dimensional. Condition 1 would also mean that the sum of the forces in the z direction equals 0. But pretty much we just can care about these first two. And also case 2, the sum of the external torques acting on the object must equal 0. Now remember, when we talk about the sum of the torques, when we talk about a torque, it's relative to a pivot. Remember, it's RF sine theta. What is R? The lever arm is the distance from F to the pivot, to the rotation axis. Remember, pivot, rotation axis mean the exact same thing. Well, let's look at first a relatively easy example. And here's an example of a, it could be a street lamp. Oh no, I'm sorry. Well, it's a floodlight in a park. And the floodlight is there's this big, huge light pole in the park. And the floodlight is attached to this light pole by this rod. This rod has a length of d. Or a beam, not a rod. It could be a rod, a beam, it doesn't matter. But it's attached to the light pole by this horizontal beam, and the beam has a length of d. And in this particular problem, we're ignoring the mass of this support beam, the beam that attaches the floodlight to the light pole. Now that's not always the case, but it's just maybe some real sturdy lightweight plastic. So we're going to ignore the mass of the support beam. Okay, so the beam is affixed to the light pole right here. It's got a width of d. The lamp is hung from the other end, and then there's also a cable that attaches the support beam to the light pole, and the cable makes an angle of theta with the support beam, and that angle is 30 degrees. Now the mass of the floodlight itself, the floodlight has a mass of 20 kilograms. And we're assuming that the support beam, in this case, we can ignore the mass of the support beam. It's a very sturdy, lightweight plastic. Well, I want to find two things. I want to find the tension in the cable that's attaching the beam to the light pole, and I want to find the reaction force that the pole exerts on the beam. What does that mean? Well, by Newton's third law, over here at this end of the support beam where it's attached to the light pole, well, the light pole, two objects are in contact with one another. They exert forces on each other. So the light pole, by Newton's third law, the beam exerts a force on the light pole, which we don't care about that force, but the light pole exerts a force on the support beam. And the support beam is what we consider to be the object in equilibrium. And typically we assume that it's fixed to rotate wherever the support beam, support rod, whatever, wherever it's affixed to like a pole or a building, that is where your pivot is. So we want to imagine what would happen if the beam could rotate about a pivot through its left end, the end where it's attached to the pole. And remember, right here at this point, at the point where the beam is attached to the light pole, right there, the light pole exerts a reaction force on the beam. And so I want to know what is the tension in the cable that's at the right end of the beam. I want to know what's the magnitude of that tension force. Remember, object attached to a cable, rope, string, there's going to be a tension force. And I want to know what is the magnitude of the reaction force that force acts at the left end of the beam. That's the force that the light pole exerts on the beam. Okay, so again, let's choose the left end of the beam right here where it's attached to the pole. That's going to be our pivot. We're going to assume that the beam, what would happen if it could rotate about that pivot? You know, what rotation would the weight of the floodlight produce? What rotation would the tension force in the cable produce? And let's call the length of the support beam D. Well, step one is identify the object in equilibrium. And for the problems that we'll see, it's going to be, in this case, the support beam. Again, we'll do another problem where you have a construction beam attached to the side of a building, and the workers can walk out on that beam and do whatever they have to do. But we'll get to that. Well, let's go ahead and let's draw all the forces acting on the support beam, as I've done here. Here's the support beam. I'll start at the right end and I'll go right to left. Well, here's the tension force in the cable. Remember, the tension force always acts away from the object but along the rope, cable, string, what have you. So the red vector, the red arrow, that's my tension force T. Well, remember, the support beam is massless, but the floodlight is not. The floodlight has a mass of 20 kilograms. So the weight of the floodlight, which I'll call WL for the weight of the light, that acts here where the light is hanging. It acts at the right side of the beam. So I have the tension force drawn as such. How did I know how to draw the tension force? It's always directed away from the object, but it's directed along the cable. The weight of the light is acting at that same point. It's acting in the negative y direction, straight down. Now, typically, right here, this R is the reaction force. That's the force that the light pole is exerting on the beam. Typically, you always draw the reaction force as if it's in Q1, as if it's in the first quadrant. Notice the reaction force, in general, will have an X and a Y component. So just the rule of thumb is the reaction force is always, it acts where the beam, in this case, where the beam makes contact with the light pole. So that's where the reaction force acts. You always draw it as if it's in Q1. Assume its X and Y components are both going to be positive. Whether or not that's actually the case, we don't care. Okay? So T, weight of the light, R. Now T and R have X and Y components. WL, the weight of the light, is in the negative Y direction. So let's get the components of R and T in the next figure. Okay. I'll start with T. Here's the tension force. It makes an angle of theta, which we know is 30 degrees. Remember, that was given. And so the y component of the tension force is T sine theta, and it's in the positive y. The x component of the tension force, indicated by the blue, that's T cosine theta. Because remember, if this angle here is theta, that angle here is theta, y is opposite, so it's sine, the x is adjacent, it's cosine. Okay, that's the x and y components of T. Well, likewise, let's get the x and y components of R. Well, so not to confuse the angles, I'm going to use the angle alpha to indicate the angle that R makes with respect to the horizontal. So here's my reaction force R. Always draw it as if it's in Q1. Now, I don't need to refer to R. I don't need to use sine and cosine. The x component of R is Rx. The y component of R is Ry. And the angle that R makes with the horizontal, the angle is alpha. Okay. Now notice T cosine theta is in the negative x. Rx is in the positive x. T sine theta and Ry, they're both in the positive y. The weight of the light, WL, the weight of the light is in the negative y. And in terms of the sum of the torques, we're choosing the point where the beam is attached to the light post. That's our pivot. And now remember, torque in general is RF sine theta. Well, remember, by definition, what is R? It's the distance from the force to the pivot. Well, any force that acts at the pivot produces no torque because there's no lever arm. The lever arm is zero. That's why you can't open the door. That's why, in terms of opening the door, the hinges are on one end of the door, the doorknob is at the other. You can't open the door by pushing on it where the hinges are because you have a lever arm of zero. So the reaction force cannot produce a torque. Okay. Because it acts at the pivot. Now let's apply the conditions for static equilibrium. What are they? The sum of the forces in the x direction must equal 0. The sum of the forces in the y direction must equal 0. And the sum of the torques must equal 0. And always apply those three conditions. Always apply them in this order. Never deviate from that. The rubric is simple. So here are my forces and components. I have T, y component is positive, T sine theta, x component is negative, T cosine theta, weight of the light is in the negative y. I have R, the x component is Rx, the y component is Ry. They're both positive. So always apply the conditions in this order. Always do the sum of the forces in the y direction equals 0. That's going to give you what I call equation 1. Then apply the sum of the forces in the x direction equals 0. That's going to give you equation 2. Then apply the sum of the torques equals 0. That's going to give you your third equation. And I had a P there, just meaning the sum of the torques relative to your pivot. You have to choose your rotation axis or your pivot. Remember, we're choosing our rotation axis to be where the beam is attached to the pole. Okay, well let's take condition the first one. Sum of the forces in the y direction equals 0. Well, a good figure saves you a lot of trouble. Notice T sine theta positive, Ry positive, WL negative. Remember, it's the y direction. Positive, positive, WL is negative. Let's add them up and set them equal to 0. T sine theta plus Ry minus WL equals 0. That's my equation 1. Now, sum of the forces in the x direction equals 0. Well, very simple. Rx is positive. T cosine theta is negative. Add them up, set them equal to 0. Rx minus T cosine theta equals 0. That's equation 2. Now let's do the sum of the torques about my pivot, about this point here, where the support beam is attached to the light pole. Well, we have, so assuming, imagine if the light pole, the support beam, if it were free to rotate about that pivot, how would the tension force, what rotation would the tension force produce? Well, it would produce a counterclockwise rotation. If you pull on the support beam with that tension force and it's pivoted here, that's going to cause the beam to rotate counterclockwise. What about the weight? Well, the weight, again, assuming the beam could rotate about this point, WL pulling down on it, it would cause the support beam to rotate clockwise. That might take some getting used to, but we'll work on that. So let's look at the torque, the positive torque due to the tension, because the tension would produce a counterclockwise rotation. Well, what is torque? In general, it's RF sine theta. It's force times lever arm times sine of the angle between them. So let's look at the torque due to the tension force. Well, the force is T. It's lever arm. It's a distance D from our pivot. And so it's T D sine theta. That's force times lever arm times sine of the angle between them. Okay? And we know it's a positive torque. Now what about the torque due to the weight? Now remember, the lever arm for the weight, let me pause this for a second. Let me just take one step back. So the lever arm for both the tension force and WL, they both act at the right end of the beam. The lever arm is indicated by this black dotted line. We know that the length of that lever arm is the width of the support beam, which is D. Right? So the lever arm for both the tension force and WL, the lever arm in each case is D. So, and we know that the tension produces would cause the beam to rotate clockwise. The weight, the WL, would cause the beam to rotate, the tension force would cause the beam to rotate counterclockwise, and WL would cause the beam to rotate clockwise. So I know the torque produced by the tension force is positive because it would produce a counterclockwise rotation. The torque produced by WL is negative because it would produce a clockwise rotation. All right, so what is torque? Well, let's look at the tension force. The force is T. We know the lever arm is D and sine of the angle between them. Now again, let's look at WL. Well, the angle between WL and the lever arm, that angle is clearly 90 degrees. Right there. That's nothing complicated. So we have TD sine theta, that's the torque due to the tension force, minus WLD, that's the torque due to WL. And they add up to 0. That gives me equation 3. Notice in equation 3, the D term will cancel. Okay, so again, always do them in that order. Sum of the forces in the y direction equals 0. Sum of the forces in the x direction equals 0. Sum of the torques equals 0. Then solve them in this order. Then go backwards. Solve equation 3 for the tension. Very simple. T is WL over sine theta. Well, what is the weight of the light? mg. So mg over sine theta, you get 392 newtons. Then you work better. Solve 3 for T. Then you go ahead. Once you know T, you solve equation 2 for Rx. Always that order. 1, 2, 3, then 3, 2, 1. Solve 3 for the tension, 2 for Rx, 1 for Ry. So now once I get the tension force, I'm going to solve equation 2 for Rx. Well, Rx is clearly T cosine theta, which gives me 339 newtons. Then you go ahead and solve equation 1 for Ry. So again, this order. Sum of the force in the y equals 0, you get equation 1. Sum of the force in the x equals 0, you get equation 2. Sum of the torques equals 0, you get equation 3. 1, 2, 3. Then solve 3 for t, solve 2 for Rx, solve 1 for Ry. That never changes. Okay, so now equation 2, I know Rx is equal to T cosine theta, 339. Solve equation 1 for Ry. I happen to get Ry equals WL minus T sine theta. Remember, what is the weight of the light? Well, it's mg. And you happen to get that Ry equals 0, which is fine. So in this case, the reaction force is totally Rx. The angle alpha is 0. In this case, the reaction force, because Ry is 0, the reaction force is entirely in the positive x direction. And so the reaction force, the magnitude of the reaction force, it's 339 newtons. And I know it acts in the positive x direction. Why? Because Ry turned out to be 0. That's not usually the case. I think it's in this case, it's because we're ignoring the mass of the support beam. But I'll do another one like this, but I'm going to put that, I'll do it in a separate video. So I'm going to try to keep the length of these videos manageable. But this is another case where here's a construction beam attached to the side of a building, and it's attached by some type of pin type connection here, and then there's a support cable attached here. And this construction beam is the object that's in equilibrium. But I'll save that for another video. Let me go ahead and stop this one and get it posted.